So this is G484 homework booklet question 5. A dotty 1 is obviously in essence just an MC delta theta question. You've just got to be careful to get the right M's with the right C's with the right delta thetas, and don't be put off by the fact they're asking you to calculate a ratio. Just work out one, work out the other, and when they've told you what sum they want you to work out. So we've got 0.8 kilograms of water with 4180 times a temperature change of 40, and for the alcohol in the thermometer we've got 0.05 times 10 to the minus 3, 0.05 grams, so just to be careful with that, times 2460, again times 40. Now just in terms of doing the sum, we may as well just cancel off those 40 degrees temperature rises, and you get through to the ratio fairly straightforwardly. 2.7 times 10 to the 3. I think the key point here is when they ask for the ratio, just calculate the ratio they ask you to. They don't want you to give it in a ratio, they don't want you to give it in a fraction. You just calculate it as a number like any other, and do make sure you get it the right way round. Do make sure you get the right one on top, otherwise that will lose you the marks that are available for that. Then asks you to state and explain a situation in which the very high specific heat capacity for water is useful. So perhaps the most obvious example is used in radiators of home central heating system, and the advantage there is the high specific heat capacity means that we get large amounts of heat for relatively small temperature rises. That means we don't need to heat the water very much in order for it to store a lot of water, lot of energy, for that to then heat the air a fair amount. Other possibilities would be a car cooling system. Again, large amounts of energy is being shifted for a small temperature rise. Or the maintaining body temperature. Large amounts of water means that large amounts of energy can go in or out of the body for a relatively small temperature rise. Cooling in a power station would be another option again, but the whole point is looking for a situation where it's good news that you can have large amounts of energy going into or out of the fluid for a small temperature rise. Moving on to part B. Describe an electrical experiment to determine the specific heat capacity of a liquid. Now you've done this experiment for a solid, and it's exactly the same. There are just a few little details that are worth picking up on. Personally, I'll draw this as two separate diagrams, one showing the situation, one as a circuit diagram. This here is representing a power supply, and you could put if you wanted to make sure the examiner was absolutely clear on that, you could put a voltage across that power supply, just right in there, 12 volts. But that's the essential idea there. And this looks like, at a glance, we've got the whole issue, as ever, it looks at a glance like an 8-mark question. It's not an 8-mark question. They split this down into 4 sections. Chances are it's going to be 2-3 marks per section. So I'll be trying to get 3 details right per section. So they've asked for a label diagram with the arrangement. There it is. There's a label diagram of the arrangement. What's worth the marks in there? For having some liquid in a container with an electrical heater submerged in it under thermometer. So there's the first mark for having the basic equipment: thermometer, the liquid in a container, and the heater inside. And then the second mark is for correctly connecting the voltmeter and the ammeter, so having the ammeter in series with the heater and supplies, and the voltmeter in parallel with the supply. So there's 2 marks, pretty straightforwardly. List of the measurements taken. Well, what do we need to measure? We need to know, I'll just move this on so you can see, we need to know the mass of the liquid. Straightforwardly, we need to know the initial and the final temperatures. You could get away with saying the change in temperature. We need to know the current, the PD, and the time. That's going to ultimately give us the energy. So there's a mark for mass, there's a mark for initial and final temperature. giving rise to delta theta, and there's a mark for the current, voltage and time. If you're trying to work out that, if you're trying to think of ways to remember it, in fact I kind of do this backwards. If you can remember how you're going to determine your value of C, that will then push you back to what readings you need. So if we start with E equals mc delta theta, we can rearrange it simply to C equals E over mc delta theta, with E being IVT, VIT. But if I remember that, I need to know the energy. How am I going to get the electrical energy? From I, V and T, so that helps me with that element of the measurements. How am I going to get delta theta? From the initial and final temperatures. How am I going to know the mass? Well, I'm going to have to measure it. So in fact, if I can remember this section here, having to do that follows very, very neatly. Now, they then got the question about uncertainties, how we're going to go about minimizing uncertainties, and as ever with these, there's a tendency for them to change their mind slightly time from time, year on year. So again, this was in the in another paper, very fractionally different, but they were interested in a number of things. Clearest one, most obvious one, perhaps being heat passing into the container. And you can allow for that if you measure the temperature of the container. Allow for this in calculations. We can have issues with the temperature going on rising after the heat is switched off, and the key is to measure the maximum value, even if that's after the heating has been finished and the timing therefore has been timed. We've got essentially the thermometer not reading the average temperature of the liquid, so it's really important that we stir the liquid. And then finally we've got heat loss to the surroundings. I would be very, very nervous of simply saying surroundings. Talk very specifically about to the air, to the desk and the rest of it. We can do that by insulating, or the better solution to that is to actually pre-cool before heating to below the room temperature, to say 5 degrees below, and then heat it until we reach the same temperature above it. And that way, when you're below the room temperature, you have got additional heat being gained from the surroundings, but that's balanced off by the heat losses to the surroundings once it's above the room temperature. So that's probably the neatest solution to there. And 2 marks for that, so you only need to pick out 2 of those possibilities. So that is a standard experiment, be it with a solid, be it with a liquid, so you do need to make sure you can remember that. In a sense, really, if you remember the key to it, remember this central part, then the measurements follow, and indeed the equipment that you're going to need is going to follow from that. And then you need to think about those losses. Do remember this heating from below technique. That does seem is a particularly neat way of getting around some of those problems. As ever, not going to have anything for repeating the experiment. The assumption is that you do it right, so it's what can you actually change in the technique, not just adding results, not just adding repeats, just in the same way as in the prac tasks. So that was G484 homework question 5.